In this video, we'll learn about two different concepts called convolution and correlation. The first one is convolution. Convolution is a mathematical operation that is used to express the relation between input and output of an LTI system. Here, LTI system means linear time invariant system. That is, if a system is linear and it satisfies the time invariance condition, then such system is called LTI system. In this subject, in the fourth unit, we will be seeing what is an LTI system, and we will only be dealing with LTI systems. We will not be dealing with any other system, right? Okay, for an LTI system, the input and output relation is given using a convolution operation, right? The relation looks like this: y of t, the output of the system, x of t is the input of the system, and h of t is the impulse response of the system. We'll see what impulse response of the system is in the fourth unit. Till then, just remember h of t is the impulse response of the LTI system. Or let me just say what is impulse response. Impulse response is nothing but when the input to the system is an impulse delta of t, when this is given as an input to the system, then the response of that system is nothing but h of t, right? This is the impulse response. When the input is the unit impulse function to the system, the output of the system is nothing but the impulse response. Okay, that is impulse response. The relation between the input, output, and the impulse response is given by this equation. The output y of t is equal to x of t convolved with h of t. Generally, we represent convolution with a circle, right? Something like this, an x surrounded by a circle, right? Don't just write x and leave it. Draw a circle around it. That is the convolution operator, right? So this is what we were talking about. The input x of t given to an LTI system produces an output that is given by x of t convolved with h of t. Now there are two types of convolution, that is continuous convolution and discrete convolution. If you look at continuous convolution, we already saw what the formula for continuous convolution is. That is integral minus infinite to infinite x of tau h of t minus tau d tau. X of tau h of t minus tau d tau. That is continuous convolution. So to convolve any two given signals, what we'll do, for one signal we will change the variable from t to tau. For the other signal, first we will change t to tau, then we will let me write it properly. First I'm going to change h of t to h of tau, right? And then I will fold this signal h of tau. So I will replace tau with minus tau, and then I will shift it by t units. So it becomes h of t minus tau, right? One signal I'll just change the variable. For the other signal I'll change the variable, then I will fold the signal and I will shift this signal. So x of tau h of t minus tau d tau. Or I can interchange these signals. Like I can just change the variable for h of tau, and I can change the variable for x of tau, and then fold it and shift it. Both are same. We can perform this operation on either h or x, and this operation on h or x. Only one signal will be shifted, folded and shifted. The other one will just be the same. Both are equal. That is, x of t convolved with h of t is same as h of t convolved with x of t. Now, if you look at discrete convolution, instead of integration, we will have summation. Summation k is equal to minus infinite to infinite x of k h of n minus k, right? Or it is also equal to summation k is equal to minus infinite to infinite x of n minus k h of k. Now these are the different properties of convolution. The first one is commutative property, which we just discussed. X convolved with h is same as h convolved with x. Here instead of x and h I have x1 and x2, right? x1 convolved with x1 convolved with x2 is same as x2 convolved with x1. Distributive property, we already know what the distributive property in algebra is. This is similar to that. Associative property is also similar to what we have in algebra. And now shifting property. If x1 of t convolved with x2 of t gives me a y of t, then x1 of t convolved with x2 of t minus t naught will result in y of t minus t naught. Shift in either x2 or shift in either x1 by t naught will result in shift in my output by t naught. If I have shift in both x1 and x2, t naught and t1 here, my output will be y of t minus t naught minus t1. This is the shifting property. And this is the convolution with impulse. This we have already seen in the properties of impulse function properties. That is, x of t, any function, when it is convolved with an impulse function, the result is the original function itself, x of t itself, right? When x of t is convolved with impulse function, the output is also x of t. If x of t is convolved with shifted version of impulse function, the output is shifted version of the input x of t. So these are the different properties of convolution. So these are some statements for convolution. Convolution of any two causal sequences is always a causal sequence. If you convolve two causal sequences, that is, if you convolve two sequences that are defined only for positive values of t, then the result is also a causal signal. The result will also be some causal signal, right? It can be looking like this, or it can look like something like this. It depends on how your input signals vary. Convolution of two anti-causal sequences is always anti-causal. For two causal sequences, if you convolve, the result is also causal. If you convolve two anti-causal sequences, the result is also anti-causal. If you convolve two unequal length rectangles, if let me say this is of length 1 and this is of length 2, then the result is a trapezium. It is a trapezium. It starts at 0 and ends at 3. It ends at 3. Right? If you convolve two equal length rectangles, if I convolve two equal length rectangles like this is 0 and 1, and this is also 0 and 1, then I get the result is a triangle. The convolved result is a triangle with these limits, right? We'll see how we'll get these limits in the next slide. A convolution of a function by itself is equal to integration of that function. Now, this is the final statement of convolution. If a convolution of a function by itself, we convolve any function by itself, the result is equal to integration of the same function. So in this slide, we'll see how do we find the limits for the convoluted signal. Right? If two signals are convoluted, then the resulting signal will have the following range. The range of the resulting signal will be sum of the lower limits, which is less than or equal to t, less than sum of upper limits. Right? Sum of lower limits will be the lower limit for the convoluted signal. Sum of upper limits will be the upper limit for the convoluted signal. If this is my x1 of t and this is x2 of t, this is x2 of t, then what are the limits for my x1 of t? It is -1 to +2, and for x2 of t I have -2 to +2. So my convoluted signal x1 of t convolved with x2 of t will have the limits. What will be the limits for this signal? Sum of the lower limits. Lower limit here is -1 and here is -2. So -1 -2 is -3, and the upper limit will be 2 plus 2, 4, right? 2 plus 2, 4. Okay, that is how we find the limits for the convoluted signal. Now let me just take an example of convolution. Let me consider one signal like this. So this will be my x1 of t. I'm defining this from 0 to, let me say 0 to 2. Okay, 0 to 2, and the amplitude is also 2. Then I'll consider my second signal. My second signal will be 0 to 1. It is between 0 to 1 and with an amplitude of 3. This is my x2 of t. This is t, and this is also t. Now what should I do according to my convolution? For one signal, I'll just change the variable from t to tau, right? From t to tau, I'll just change the variable. How does it look? It looks something like this. From 0 to 2, this is tau now. The amplitude is 2, and this is x1 of tau, right? For the second signal, I'll change first from t to tau, so it looks very similar to this. 0 and 1, then amplitude of 3. Then I will fold the signal. That means in place of tau, I'm going to write minus tau. In place of tau, minus tau. Now it looks like this. How will it look when I fold the signal? So this is my 0, and if I fold, this comes to this side. So from 0 to minus 1 is an amplitude of 3. This is my x2 of minus tau, right? Then finally what should I do? I should get x2 of t minus tau, right? That is according to the formula of convolution, right? What is my formula of convolution? It is x1 of tau, x2 of t minus tau d tau under integral minus infinite to plus infinite, right? That is my convolution formula. So now I have to shift this signal with t. If I am adding a positive number t, the shift will be towards which side? It should be towards the left side, something like this, right? I am shifting it by t. So where the value at 0 here, it will be shifted t times, right, by t. So this will be t, and this will be t minus 1 with the same amplitude of 3, right? Same amplitude of 3. Now first I will find the overlapping regions. So let me take a different color. This is my x1 of tau. X1 of tau. This is my x1 of tau, and my x2 of t minus tau is at present somewhere here, right? This has an amplitude of 3, and this has an amplitude of 2. So the limits here are t and t minus 1. So if you look here, when t is less than 0, when t here is less than 0, there is no common region between the two signals x1 and x2, right? So when t is less than 0, there is no overlapping region. Let me write that in a different color. I will take this. Overlapping regions, right? Overlapping regions. So when t is less than 0, there is no overlapping region. There is no overlapping region. Now I will shift this t. I will shift this x2 of t minus tau little towards the right hand side, such that there will be some overlapping, right? So how do I draw that? Something like this. It just starts to overlap, right? It just starts to overlap. So this is my t minus 1, and this is my t. So this is my overlapping region, right? This is my overlapping region. So what is the condition here? T minus 1 is less than 0. T minus 1 is less than or equal to 0, and t is positive number, right? T is greater than 0. If I simplify this, what will this be? T is less than or equal to 1 and T is greater than or equal to 1, right? It can be equal to 0, no problem. So my second overlapping region will be T in between 0 and 1. Sorry, this must be 0, right? Sorry. So T in between 0 and 1. This is my second overlapping region. Then my third overlapping region, how will it look like? My third overlapping region, I'll just move the second signal x2 of t such that x2 of t such that both the limits now are on the positive side. Both the limits now are on positive side, something like this. So this will be my t minus 1 and this will be my t, right? So my both t minus 1 and t now are positive, right? Both are positive. So what will be my limits now? T minus 1 is greater than or equal to 0 and t is greater than 0, yes, but it is less than 2. T is less than or equal to 2. So if I simplify this, t is greater than or equal to 1 and t is less than or equal to 2. So my third region, my next overlapping region will be 1 less than or equal to t less than or equal to 2, right? So this is going to be my tau. So instead of t, I will write tau. Instead of t, let me write tau. Right? And finally, I'll move this second signal further. If I move it further, how will it look like? How will the overlapping region look like? If I move it further, something like this. This will be my t minus 1 and this will be my t. So t minus 1, now what will be the condition here? T minus 1 is less than or equal to 2 and t greater than or equal to 2, right? Greater than 2, greater than or equal to 2. So now when I simplify this, t minus 1 what will I get here? T is less than or equal to t is less than or equal to 3 and t is greater than or equal to 2. So my third overlapping region is going to be 2 less than or equal to tau less than or equal to 3, right? Right? Then finally, if I shift the x2 further, it will be something like this. Now this is t minus 1 and this is t, right? When t minus 1 is greater than or equal to 2, there is no overlapping between the two signals. That means t is greater than or equal to 3, no overlapping. So when tau is greater than or equal to 3, there is no overlapping, none, right? So these are the three overlapping regions. Now for each of the overlapping regions, we need to find the convolution. So again, let me draw for the first overlapping region. What is the first overlapping region? It is 0 less than tau less than 1. It was something like this, right? It was something like this. This was my t minus 1 and this was my t. So this was the overlapping region. So what is the convolution formula? The common region here is integral. The common region is 0 to t. So lower limit is 0, upper limit is t. The first function amplitude is 2. Second function amplitude is 3 x2 of t minus tau. The amplitude is just 3, right? And d tau. So simplifying this, we get 6. Integration of d tau is tau and the limits are 0 to t. So the final answer is going to be 6t. This is for the first region. For the first region, y of t, which is nothing but the convolution of x1 and x2, is equals to 6 into t. For the second region, so I'll draw it here. This will be my second region. Something like this. This is my t minus 1 and this is my t. So now this is the common area, right? So what are the limits for the common area? It is t minus 1 to t and two amplitudes, 2 into 3 d tau. So that is nothing but 6 tau. Lower limit is t minus 1 and upper limit is t. So 6t minus 6t minus 6. So these two get cancelled and the result is 6. So now y of t in this region is 6. Okay. Now let me erase some stuff and we'll find the convolution for the last overlapping region. For the last overlapping region, we have something like this. Something like this, right? So here, this is t minus 1 and this is t. So my overlapping region is this, right? So integral, my lower limit is t minus 1 and upper limit is 2. Upper limit is 2. And my amplitude, x1 of tau is 2 and x2 of t minus tau is 3 and d tau. If I integrate it, I'll get 6 tau with limits t minus 1 and 2. If I substitute 2, the upper limit, it is 12 minus 60, 12 minus 60 minus 6. So the final answer is going to be 12 plus 6, 18 minus 6t. So here y of t is equal to 18 minus 6t. Okay. Now we'll draw the final convoluted signal graph. So this is how we'll find the convolutions in each overlapping region. And then let me draw the final convoluted graph. So this is 0, 1. Look at my regions. Less than 0, 0 to 1, 1 to 2, 2 to 3, and greater than 3. Right? This is my y of t. And this is t. So less than t. Okay. Okay, when t is less than 0, there is no overlap region, so the value is 0. The value is 0. Between 0 and 1, y of t is equal to 60. So at 1, when t is equal to 1, y of t is 6, right? This is somewhere here, 6. So I'll just draw a straight line, it's linear. And then from 1 to 2, y of t is 6, it is constant. So 1 to 2, it is 6. And from 2 to 3, it is 18 minus 60. If I put t is equal to 3, 18 minus 18, it is 0. So it will join here, right? This is a straight line. It is a little difficult to draw straight lines here, but you have to draw a straight line. And finally, when t greater than 0, it is again 0. There is no overlapping regions. So it is 0. So this is my final convoluted signal. So look here. These are two rectangular signals of unequal length, right? One is of length 2, the other one is of length 1. So our final result looks like a trapezium, right? Does it look like a trapezium? Yes, it does look like a trapezium. That is what we have seen in the last slide here. Let me show you that. That is what we have seen here. Convolution of two unequal length rectangles results in a trapezium, right? If you take two equal length rectangles, it results in a triangle here, right? Now we have seen this. So that is how we perform convolution of two signals graphically. Now let's move on to the next type of convolution. So far what we've seen is continuous convolution on a continuous signal. Next we have discrete convolution. So discrete convolution, x of n is given and h of n is given, right? So it's very easy to perform discrete convolution. So I'll take a matrix method. This is a matrix method. I'll take x of n here on this side and h of n on the other side, right? X of n is a, b, c. H of n is e, f, g. So I'll just multiply A with E and write here AE. Next one is going to be AF, and next one is going to be AG. Multiply A with the corresponding values in H of n. Now with B. B with E. BE, BF, BG, CE, CF, CG, right? And then I'm going to draw certain lines. Look, this is one. I'm going to draw lines like this, right? So this is how I'm going to draw lines. And now my final result is going to be my y of n is going to be something like this. First element will be AE, comma, the next element is going to be AF plus BE, the next element is going to be AG plus BF plus CE, the next element is BG plus CF, and the final element is CG. CG, right? AE, AF plus BE, AG plus BF plus CE, BG plus CF, and CG. This is my y of n. So x of n is of length 3 and h of n is also of length 3. Now what is my length of y of n? Y of n length will be length of x of n plus length of h of n minus 1, right? This is the formula for length of discrete convolution. The length of the first signal plus the length of the second signal minus 1. So here 3 plus 3 minus 1, 5. So we have 1, 2, 3, 4 and 5. Right? That is how we perform discrete convolution. This is an example of discrete convolution. Right? I have minus 1, x of n is minus 1, 2, 2 right here. And this is my x of n minus 1, 2, 2, and this is my h of n 1, 2, 3. I'm multiplying the corresponding numbers. Minus 1 into 1 is minus 1, minus 1 into 2 is minus 2, minus 1 into 3 is minus 3. And similarly for the other two rows. And I am drawing these lines here. And my y of n will be, the first element will be minus 1. The second element will be minus 2 plus 2, that is 0. The third element will be minus 3 plus 4 plus 2, that is 6 minus 3, 3. Then 6 plus 4, 10. Then 6. So the length is 3 elements here and 3 elements here. So total 6 minus 1, 5. So my final output must have 5 elements. Then correlation. Correlation is a measure of similarity between two signals, which means the value of correlation will tell me how similar are these two signals x1 and x2. This is the general formula for correlation. Again, there are two types of correlation: autocorrelation and cross correlation. Autocorrelation means correlation of a signal with itself. We are going to correlate one signal x with itself, with x only. So it is actually a measure of similarity between a signal and its time delayed version. So this is the formula for autocorrelation. We denote it with R of tau. Since it is auto, because it is for the same signal, correlation of the same signal, 1 and 1, right? Auto means I'm calling the signal as x1 of t or x of t. So R11 of tau denotes autocorrelation. We also denote it with R of tau. The formula for autocorrelation is minus infinite to infinite x of t minus tau dt. Suppose if the signal is complex signal. If the signal is a complex signal, the formula is almost the same one with just a complex conjugate for the shifted version. Similarly, cross correlation. Now we measure the similarity between two different signals. Previously, autocorrelation, we measured the similarity between the signal and its time delayed version. Now it is between two different signals. One signal will be x1 of t and the other one is x2 of t minus tau. Unlike convolution, which is commutative, we can interchange x1 and x2. Correlation, we cannot interchange x1 and x2. If we interchange x1 and x2, we'll get a different result. So R12 of tau is not equal to R21 of tau. Okay. Then again, if the signal is complex, we'll just take the complex conjugate of the second signal. These are the properties of autocorrelation. You can just go through the properties of autocorrelation and cross correlation.